So this example shows you the magnetic field patterns for a bar magnet. And we're going to look at, so this is a single, so this is just a single, and this is two bar magnets. And here, if you can see that if this is the north and this is the south, then you can have some kind of pattern of field lines that, and those field lines are always coming out of the, so coming out from the north and going into the south. So this is the north. Now, you have two bar magnets and you place them in such a way that this is the north and this is the south here. Then you have field lines going like that. Again, always going from the north to the south. And if this is north and this is north, then you see that the field lines are kind of coming out like this. So this is an example of a repulsive force. This is an example of an attractive force. Now, so the way to explain this is that you can think about, so the north is almost the same as the positive charge, and the south is almost the same as the negative charge. So it means that when you have a north and a south, you're going to experience an attraction. If you have a north and a north, you get a repulsive force. Now, so the Earth has a natural, is acting as a natural, the magnetic field of the Earth is pretty weak, it's about 10⁵ Teslas. And again, you can think of the Earth as some kind of like a giant, just that the magnetic field is pretty weak. So now, again, as I said last time, we're going to be looking at the particle in the magnetic field. And the way we're going to solve this, we're just going to say that assume that the magnetic field is given, so B is given. And I want to ask myself, how does a charge move in presence of the magnetic field? So that's what we're interested in. And we're going to see that, so the magnetic force is proportional to the charge Q. The magnetic force on the negative charge is acting in the opposite direction compared to the magnetic force of the positive charge. And the magnetic force is also proportional to the magnitude of the magnetic field vector. Now, if you take all of this and put it together in an equation, you get this equation right here. And I think I already went over this equation from last class. We said that, so the magnetic force, when you calculate the magnetic force here, Q is the charge, and V is the velocity. And V is the magnetic field. Say that we need to calculate this by taking the cross product. So let me just go over this real quick because, and then I gave you this simple equation to remember here. I said that if you remember this picture here, always going in the counterclockwise. So counterclockwise is considered a positive direction. clockwise. So going from I to J, then we have all these equations. I guess you guys can do that because we've done about some examples. Now, sometimes, if you wish, you can also use this equation here. So if you want to calculate the cross product, you can use this equation here. I'm pretty sure you guys have seen this in one of your math classes. So let me stop here, and then let me go to let me share this other screen here so I can look at one example here. Let me share my other screen. Now, so when do we use this equation here? So A cross B, so vector A cross vector B is given by this equation. So I, J, K, AX, AY, AZ, BX, BY, BZ. Now, let me give an example. Suppose that we have a charge Q. Let's just say that this charge is 1.60 times 10 to the negative 27. And then let's suppose that the velocity vector to the 5 meters per second to I is 3J minus 4K. And the magnetic field is given by 0.5 Teslas. The pointing in this direction here, I had. Now, if you have something like this, then this would be the best type of problem where you can use this. Like you can use this this equation right here. You guys see that? Because in this case, for example, if I want to do this calculation here, then because I know that the force is, my magnetic force is equal to QV cross B. So I can multiply the charge by this, then multiply that by the strength of the magnetic field. Okay, so if you do that, you get, so that should give you, so 10 to the power 5 and 10 to the power 27 should give me 10 to the negative 22. And then we're multiplying 0.5 times 1.6, that's 0.8. So you end up with 0.8 times 10 to the negative 22, which is the same as 8.0 times 10 to the negative 23. So all of this is equal to 8.0 times 10 to the negative 23. And then you want to calculate this determinant here, I, J, K. Now, you're going to put 1, 3, negative 4, and then 1, 1, 0. Does that make sense? Now, do you see why for the magnetic field you put 1, 1, 0? Because the magnetic field does not have any component in the K direction, right? So it only has I and J, and there is no K. And so now you can go ahead and use the rules for calculating the determinant of a matrix. You can solve this problem. Yes.
In Calc 3, like we did this like a couple weeks ago, and whenever you do the next step, you do minus the J term.
Yes.
But it's plus in here.
Right. Yeah.
Okay.
So there is some signs. So for example, this goes, so the I goes with positive, the J goes with negative, and the K goes with positive. So for example, say that this is I hat into then. So the way you do it is that you close this row and that row here, and then you calculate the determinant of this, which is AY BZ minus AZ BY, right? And then the next term is negative J hat. And then when you calculate J hat, you're going to close up this row and this row here. So this would be AX, so AX BZ minus AZ BX. And then finally, you take this row, this column here, or this column and this row, and then you calculate that determinant of plus K hat into AX BY minus BX AY, something like that. So there is some rules.
Just in the PowerPoint, it has
Yes.
like plus K. I'm just confused about that.
Yeah. So this is when you may decide that you want to use this equation, but if, let's look at, so what if I have a very simple example where it just tells me that the, again, let's say this is equals to 1.60. Let's say this is 10 to the power 5 meters per second. .5 Teslas pointing into the Ki direction. Now, if I have something as simple as this, I can just calculate this using my rules here. So again, this is I, and this is J, and this is K, and we know that counterclockwise is positive. Because if you want to do this, you can just, so you take I and K, and then J and K, right? So it means that when I do this calculation here, this would be one, so the force, the magnetic force is going to be Q, B cross B, which is equals to 1.60 times 10 to the negative 27. Then let's factor out this times 10 to the power 5. And let's factor out this times 0.5. And then all of this is going to be multiplied by I hat plus 3J. And I want to cross this with K hat. And then this is where I'm going to go in and say that when I cross this, I can cross I and K, and then I can cross J and K. Now, do you see that when you cross I and K, what do you get? J. Because going from I to K, we're going in the clockwise direction, and clockwise is negative, right? How about J and K?
Plus 3I.
J and K is plus I. So this is plus I. So my final answer here is going to be, so if you multiply this out here, this will be 8.0. 10 to the negative 23. And then you have into 3I hat minus J. All of this will be in meters. So in what direction is that force acting? So if you have a force where the X component is positive and the Y component is negative, what does that tell you about the direction of the force?
104.
It's right there. And if this is the force, you see that the velocity is somewhere like that. And what is the magnetic field? It's coming out of the paper, right? So the magnetic field here is dot like this. So you have a magnetic field that is coming out of the paper. You have a velocity that is pointing in the northeast. Then the force should be pointing more in the southeast. And you're going to see that this force is always going to make 90 degrees with respect to the velocity.